In the previous lessons, we learned how to use the periodic table to determine the relative size of different elements on the periodic table. In this lesson, we are going to look at using the periodic table to determine the relative ionization energy. So, ionization energy. Now, what is it? Well, it is the amount of energy required to remove. Now, what does the word remove mean? Well, think about losing an electron, right? If your electron is being removed, you're going to lose that electron. Well, which electron is going to be removed? Of course, from the most loosely bound electron. And this right here is your valence electron from a gaseous atom. Well, it has to be in a gaseous state in order for that electron to be easily removed. Up here, I have the data of ionization for the first electron in that particular atoms, and it's based on the periodic table. As you know, we have period 2, 3, 4, 5, 6. So let's look at the trends for first ionization energy. That is, remove the first electron from an atom. Before we look at the trend, we have to look at in terms of the size of an atom. And look at this. We know that inside an atom we have a proton that's attracting the electron, right? That's pulling the electron in. And this is the valence electron. So there's a distance right there. And in this smaller atom, compared to a larger atom, here you have your proton all the way in here. Look at the distance. This is larger and this is smaller. So of course, if I were to take away an electron from a smaller atom, see right there, it is shorter. So therefore, think about it. That proton's gonna pulling onto it. So this shorter distance requires more energy. Where if you look at the larger atom, the distance is farther away, okay, or larger. That means the attraction of the proton on that electron is going to be weaker, so it's going to require less energy. So that's the understanding of how proton and electron attract each other. So let's look at this. In a smaller atom, we observe that here, a positive nucleus is closer to its valence electron, as you can see there, so it requires more energy to take away an electron from that nucleus or an atom. So now let's look at our data. Well, this is within a period, right? We have lithium right there. So go back to your periodic table. This is period 2. And going across, what happened to the atomic size? We know that atomic size decreased. So that means it's getting smaller. So over here, it is smaller. Well, if that's the case, that means the atomic size decreased. In terms of ionization energy, it would be the opposite. So I'm going to abbreviate INE. That's for ionization energy. It would increase. And that makes sense because the size is getting smaller. So INE will increase. So moving from left to right across a period, ionization energies increase because the atom size decrease. So again, ionization energy is abbreviated by IE to make it easy for us. Now let's prove this with our data. So here we have lithium going across. Look what happened. In relative trend, what happened to the ionization energy? Of course, from 500 all the way to 2000. It would increase. So this is period 2. What about period 3? So period 3 is from sodium all the way to argon. What do you see? Well, look what happened. It also increased. So that's how we interpret this data, proving to us that going across the periodic table from left to right, ionization energy increased. Now, in a larger atom, which we observe here, okay, a positive nucleus is farther away from its valence electron, which we observe there. This distance to here is a lot farther away compared to the small size atom. So it requires less energy. And that's because the proton from all the way inside couldn't attract the outermost electron to take away an electron from that nucleus or atom. So if that's the case, remember in the back of the day when we go down the periodic trend, right? The atomic size increase. If that is the case, if we're getting larger going down, that means I and E would do what? So, well, I and E would have the opposite trend, because now the larger the atom it is going to be, that nucleus is not going to have that stronger attraction on the outermost electron. So I and E would decrease going down. And that's what we have here. Moving down a group, ionization energy decrease because atom size increase. Because in a larger atom, the distance between the nucleus and the outermost electron are greater, so therefore they don't have that attraction. So it's easy for that electron to be taken away. Now, the trend that we are talking about is just talking about the first ionization. It's about removing the first electron of an atom. But we can remove multiple electrons from a single atom. And we have the term something called second ionization energy. That is the energy required to remove the second electron. Okay? So if that's the case, how is that compared to the first ionization energy? Well, in most cases, the second ionization is higher than the first ionization. So think about it. If you remove an electron, now you have less electron in your atoms, right? And what does electron and electron do to each other? They repel. So fewer electron, that would decrease the electron repulsion. So now the proton will hang on to the remaining electron. So let's try an example problem. Rearrange the following set of atoms from highest to lowest ionization energy. Well, in this case, boron, nitrogen, and fluorine right here. So we have boron right there, nitrogen, and fluorine. That's the first thing you need to do. Find where they are on the periodic table. Well, if we know the trend going over this way, it would increase. So from the highest to the lowest, of course, the high would be all the way over here. The highest would be fluorine, okay? Followed by what? Nitrogen, and followed by boron. And if we think in terms of atomic size, the highest one would be the smallest, and the lowest one would be the largest. And that makes sense. If we apply the periodic trend, boron would be the largest one. And that's why it has the least ionization energy. Let's try another one. Sodium, potassium, and lithium. Well, sodium, potassium, and lithium. And we know that going down, what happened to ionization energy? It would decrease. So the one all the way to the bottom will be the lowest. In this case, the highest one will be on the top. So we have lithium will be the highest, followed by sodium, followed by potassium. And this right here is your largest size as well. Okay, so keep that in mind. It's the opposite of atomic size. Now let's try another set. Well, in this case, we are rearranging from lowest to highest ionization energy. Well, nitrogen, lithium, and boron. So in this case, we have nitrogen, lithium, and boron. So going from lowest to highest, remember, going across what happened to I and E. Ionization increase. So the lowest one will be all the way over here. Of course, that would be our lithium right there. Okay, followed by what? It's gonna be our boron. So boron would be the one, and followed by, lastly, nitrogen. And if we look in terms of atomic size, nitrogen is also your what? It is now your largest one. So you now have different trend to verify your answers. Okay, so keep that in mind. Let's try the last one, calcium, beryllium, and magnesium. So calcium, beryllium, magnesium. Now, remember, we're looking for the lowest to highest, so going down, it decreased, so the lowest one will be on the bottom. So we have calcium, that will be the lowest one, followed by what? Magnesium, and lastly, followed by beryllium. And that is how you apply the ionization energy and looking at the periodic table to determine the relative amount of energy required to remove an electron from that atom.